So selection on single and multiple traits. So let me think about this for a second. We're going to do this. We're going to do this in 2 lectures. This lecture is going to be just sort of about the descriptive aspect of selection coefficients, and then we're going to have another lecture on selection as a surface. So I'm trying to build to that lecture in perspective. So a natural way to think about selection is a surface. But we're not just going to leap there. We're going to take a little bit of time and think about the non-selective sort of old, what you might think of as the older, not illegitimate, but older way of thinking about selection. So, but this is all good background for when we get to the selection as a surface thing. And then tomorrow we're going to do an exercise in which we estimate a surface and even bootstrap it. So it'll be fun. All right, so here we go. And my icon today is, I would quiz you, but I photographed this bird in Cameroon last month. And I like it as a photograph. And I put it up here as an icon because it reminds us that there's a lot of field work that has gone into estimating selection and exactly the kinds of selection coefficients we're talking about here. And this is a picture of the blue-billed malimbi in Central Africa, and that's Tom Smith's hand. It must be his right hand holding it. And I like this picture because if you look at it on your laptop, you may be able to see the mist net in the background where it was caught that morning. And so these selection studies that you see, and we'll refer to a couple of them, are each a labor of love. It's excruciating to get a big enough sample before and after selection. And a lot of us have done these studies. It's very easy to put a lot of work. I put a lot of work into mark and recapture with snakes 6 years and didn't get anything significant out of it. And you just sort of go, darn. But there are, for I don't know how many, for every failure like that, there are successes like Tom Smith studied, not of this species, but other finches. But this is a beautiful bird, and you can see you can still see a very important character, the beak depth, which has been much studied in Galapagos finches. We're actually going to talk about it later. But at any rate, there's a lot of interesting field work that has put these measures of selection to good effect. Okay, so here's our thesis. We thought selection changes trait distributions. We talked about distributions before and after selection. We're going to look at the distributions. And because of the first point, the contrast between distributions before and after selection provides a powerful description of selection. And we're going to talk about that contrast, not the contrast between survivors and non-survivors, but the contrast between before and after. That's the more powerful statistical comparison. We're going to see why that's so. We're also going to see that multivariate measures of selection can correct for correlations between traits when we go to the multivariate world. We not only have these correlations exerting effects, but we can correct for them. And this is the standard. How many of you have taken multivariate stats? Raise your hand. And so if you think back to multivariate stats, when you have correlations and you correct for them, you go from multivariate space to univariate space. Do you remember what every one of those equations has? The inverse of a variance-covariance matrix. It's the standard way of going from multivariate to uncorrelated characters. Simple correction. And guess what we're going to see right in the middle of our we're going to see the inverse of a variance-covariance matrix. So this is a familiar statistical path that we're going to trundle along. Okay, so here's our outline. We're going to start by looking at how selection changes univariate trait distributions. We're going to look at several different coefficients: little s, big C, beta, and gamma. S is the shift in the trait mean, the so-called linear selection differential. We've been exposed to it before. We're also going to talk about C. If we look at the change in the mean in the univariate space, it's natural to look at the change in the trait variance. We're going to call that C, and we're going to call it the nonlinear selection differential, just the analog of the second moment analog to S, the first moment change. We're going to look at, then 4, we're going to look at examples and surveys of univariate selection differentials. And then 5, we're going to look at how selection changes the multivariate trait distribution. And we're then going to introduce 2 multivariate measures of selection. One we've already talked about briefly, that's beta, and we're going to call it by name the directional selection gradient. It's going to be a vector. We've already seen it as a vector. The vector with elements equal to the number of traits. The new thing we're going to talk about today is gamma, the nonlinear selection gradient, and it's a matrix. And it's going to tell us how selection acts on variances and covariances. It's the matrix that tells us about how selection is producing morphological integration, for example, or phenotypic integration in general. And then we'll end with some examples and a couple of surveys, not as many as we'd like. Okay, selection changes the univariate trait distribution. Let's look at, this is a hypothetical example. We've got a trait distribution. This is drawn from a normal distribution. It's not surprising that it looks normal because, you know, we sampled from a normal distribution to get this. And then let's imagine that we perform truncation selection so that only the black individuals become the sample after selection. Here's the sample before, and I've included the blue ones. Drop them off. This is the sample after selection. Suppose we just want to compare, contrast samples before and after selection. The way that we've done this before is to look at the selection differential, the change in the mean, and let me get my pointer here so I don't walk in front of the screen. We're just here applying our formula, C bar star minus C bar. That gives us, that's the shift in the mean, right? Distribution, the mean after selection, the mean before selection. Here's the mean after selection. The mean before selection, even though I sampled from a normal distribution with a 0 mean, you know, it's not quite 0, it's minus. Anyway, so we get a selection differential of 0.07. In other words, we shifted the phenotypic mean by 17% of one phenotypic standard deviation. So the variance was 1 before selection. All right, so now I'm going to do a terrible thing to you. I'm going to take you back to your calculus course. So the good news is, I don't know if it's good news, but I didn't like calculus that much when I took it. I love it now, but we're just going to take integrals. We're going to integrate, but we're not going to differentiate. Okay, so there's a general way of thinking about the selection differential. In the case of viability or survivorship, then the sample after selection is easy. Those are survivors. But in general, selection could shift the population in any way, and it might not just be a distribution of survivors. It might be individuals that are weighted by some other aspect of fitness, and that's what our general formulation is going to tell us. So let's in integral formulation, this is Landy notation, incidentally. So it's a little stripped down. We're not saying what the bounds of integration are here and so forth. It's all implicit. Z bar is the average of the distribution before selection. So if the trait is Z and P of Z is its distribution before selection, then the mean is just we just take the integral of trait values weighted by their representation in the population, right? And that P of Z integrates to 1, right? And so this gives us the trait average. It's a familiar formula for, think of it as sigma notation, right? Think of that as sigma without D of Z at the end. Then we'd be summing all of the trait values, and we could, instead of having all of the trait values lined up, we'll take all the individuals with a particular trait value, and we'll multiply them by their frequency, right? That's what we're doing here. But we're doing it not with many bins of very small size, right? That's what calculus is all about. Okay. So it's not surprising then that the mean after selection is the frequency of each phenotypic class after selection as a weight for each phenotypic class, right? It's the same formula, but we've got a different distribution. The distribution has changed, and we need that new weight. So what we're going to say as a general formulation is that new weighting is each phenotypic class frequency before selection is weighted by relative fitness, which has a mean of 1 and just as a matter of definition. And that's what P of Z is. It's the original class weighted by fitness. So the lovely thing about this is we played a cost in comprehension because we went to our integrals, dredging them reluctantly out of our deep memory perhaps. But nevertheless, you all took calculus. The prize here is now we have a general definition for the distribution after selection, a completely general way of thinking about selection, and it's just a question of what kind of fitness component W of Z here. You're standardized, so you've got a mean of 1. Okay, completely general. Sexual selection, viability selection, fertility selection, any kind of selection you want. Now, next time, what we're going to talk about is that this W of Z is a fitness value, relative fitness of the Z phenotypic class. In general, there might be a nice functional form for W of Z. That might be a nice continuous curve. And that's what we're going to talk about next. W of Z as a function might be a nice simple thing. Yeah.
Assume that the trait value doesn't change because of selection?
In an individual? Yes, it does. So you keep the same trait value, but you as a class with phenotypic values Z, your frequency, your figurative frequency, it might not even be observable without measurements, right? Your representation might increase because your class lays more eggs, but your physical presence looks the same. You with me? That would be fertility selection. All right. All right, so a consequence of this is, and this is a result first shown by Alan Robertson in 1966, is that our selection differential turns out to be a covariance. And here's the standard. I'm just going to skip through this. But at the end of the day, what you can show is that our shift in the mean, S, is equivalent to the covariance between two random variables, relative fitness, W, and the trait value before selection. True fact. Now that turns out to be why S is so useful to us, because S is a covariance, and covariances can be estimated, and they have known roles in multivariate statistics. S for us is a vector of covariances. And that's why we're contrasting the sample before selection and the sample after selection. That makes our contrast, means our contrast will be a covariance, and that's going to be very useful to us. And this is not a hard thing to convince yourself of. I'm just not going to take time to do it, because we want to go to lunch at 12:30. Okay, similar arguments apply to the contrast in variances before and after selection. So think of a new measure of selection, let's call it C. It's the difference between variance after selection and variance before selection. Now, here's a tricky thing, and that is we're going to add a correction term, S squared. And I'm going to explain why we do that in a minute. It's going to turn out that by adding this correction term, this contrast in variances plus the correction term is going to be equivalent to a covariance. But P star minus P doesn't have that property. Okay? So what is this thing S squared that we're going to add in there? We're going to wonder about that. But for right now, knowing this, we're going to define our coefficient C in this way. And so for our data set, it turns out that our measure of C is minus 0.24. That is to say, there's a contraction of variance. Our variances were 1, so we can, before selection. So this contraction is like a 24% contraction in variance once we do the correction S squared, which we're going to talk about in a minute. And as before, in integral form, what is a variance? Well, it's just squared deviations in the mean multiplied by their representation in the populations, right? If we take the average of all of those, that's a variance. But for one thing, why is it unfamiliar? Why is this slightly unfamiliar? There's no n minus 1, right? Because this is the parametric value for the variance, not the estimate. And Joe would like to say a few words about why the estimate of this variance has a denominator of n minus 1.
Well, actually, I'm not going to say that, but I'll say that, yes, it has an n minus 1, it's just that n is infinity.
Yes, okay, that's a good way of putting it. Yeah. All right, that's a good point. But isn't n minus 1 the maximum likelihood estimator of the?
I think there's some difference between ML and REML, and we don't have time for it because lunch impends.
It's approximately true, but yeah.
It's approximately true.
So sometimes when Joe says you're wrong, it just means that you're approximately right, not absolutely right. So don't despair. Okay, so what is this S squared thing? Well, it turns out that that's the amount that the variances say contracted. Well, it's contracted by linear selection of magnitude S, and we have to describe what linear selection is. So if you want to think of how much variance is contracted other than by just regular linear selection, and this will become clear in a second, that correction term is S squared. So what happens is what happens, this is a result published by Landy, and I was happy to be a co-author in 1983. And so I drank a lot of coffee trying to be what would you call it, a conscientious co-author. And so what actually happened is Landy was hoping this would be the covariance, but it turned out to be this S squared term. And you go, what the hell is that there? What is S squared? And then you figure out, it's how much selection would be contracted by a linear. So that's how the derivation dropped out. But it's just, if it's important for S to be a covariance, it's also probably important for C to be a covariance, right? And that turns out to be true. Okay, so here's our point. I've already alluded to it. C is a covariance, but P star minus P is not. And so to make it a covariance, you've got to have that correction term, and so it's worth getting that there. All right, so here, this is actually a term that we're gonna use. We're gonna use Z squiggle, which is just the deviation of a trait value of an individual's trait value from the mean before selection. It just makes writing this covariance a little more compact. And we're going to do that standardization just to make some of our estimation procedures a little faster. Okay, let's just look at a couple of examples before we rush on to the multivariate case. Here's an example with, this is the, let's see if I have to think, Geospiza fortis on Daphne major in the Galapagos. It's like our standard example from Peter Grant and Rosemary's team. This is Trevor Price doing a lot of the field work in those years. And here's the distribution of beak depth before selection. Here it is after an episode of viability selection occasioned by a drought. And so that's the distribution after selection. And here's the shift in the mean. Now I would have drawn it as a nice short arrow, which is more accurately represents S, but okay. So that's S. There's also a change in the variance here, which I haven't diagrammed. All right, so we can also standardize. The shift in the mean, and there are a couple of ways to do this. One of the ways to do it is standardize all the traits so that before selection, they have a unit variance, or after you calculate S. Here's the difference in means before and after selection. You can divide by square root of p. What is square root of p in our notation? It's a little awkward, but I could have said p to the minus 1/2. Yeah, p to the 1/2. What is it?
Is the standard deviation of the trait?
It's the standard deviation of the trait. Just a little awkward to write, but we're going to use the variance so much more that this is the price we pay for doing that. Okay, so if you're looking at different traits, let's standardize all the traits so that so now when we look at the shift in the mean, it's in units of phenotypic standard deviation, right? And now we're going to compare 262 studies that estimated this standardized selection differential. These are Endler's data, and you can see that, incidentally, S could be positive or negative. We've taken the absolute value, so we don't have and so now it's, just the absolute shift in the mean, and you probably can't see the scale, but this is, I guess this is 1.9 phenotypic standard deviations. So it's extremely uncommon to shift the mean by more than 2 phenotypic standard deviations within a generation, right? It's a pretty big sample. And you can see most of the time you get, a 5% or less shift in the mean. And then it looks like a negative exponential distribution. Okay? So most of the time you're just having little shifts in the mean. So this is I need a name for this. Let's call it today the Arnoldo graphic. So, so in blue we draw the distribution, a normal distribution with a standard deviation of 1 before selection, and then each of the black curves represents a distribution after selection. And so what I've done is I've taken this bin, and that's the first curve, and I've weighted it in proportion to its frequency, and then I've gone out here to the first 5 or 6 bins. And so the point is that the shift in the mean that we're observing empirically is very, very slight. It's not a big jump. It's just a little nudge in the mean. That's the common observation. And that's an important piece of information. We'll come back to it later. Likewise, the same thing with the corrected shift in the mean, the C, we're going to call C prime when we corrected for phenotypic variance before selection. So now this is in units of so when I say here, let's look at this. This bin right here, this point on the curve would be minus 0.35. That means that we've contracted the variance in the trait after correcting with the S squared term by 35%. Or here we've expanded the variance by 55. Or here we've almost doubled the variance, right? So basically what you see is an almost symmetrical distribution. I meant to come back and add a line for 0, which I think would be just about here. I meant to put a dotted red line in there. So actually cases in which this is, sorry, this is a good point. This is minus 0.5 here for that bin. So actually the line would be right here, right? So all of these cases, there's contraction of variance, and in all of these cases, we have expansion of variance. So this looks like what? Over here. From the big mode down. Those are cases of stabilizing selection, particularly if we close the mean. And these are cases of disruptive selection. There's a lot of disruptive selection happening out there, but the predominant pattern would be, well, I don't know, if you integrate the two, they're about equal in outcome. And if you look at the Arnoldo graph, you can see that the cases of contraction actually outnumber the cases of expansion, right? But in any case, variances are not hugely affected. Where most of the spread is like plus or minus 30% change, and a lot of it's minuscule. Okay, point 5. Now we're going multivariate. Now we're going to talk about our two coefficients, beta and gamma. We have a half an hour to do that. Maybe we can do it in less than half an hour. Okay, so now we're multivariate. And let's just take, I'm going to sample again from a normal bivariate normal distribution. And I'm setting it up so this is the P matrix. Variances of both trait are 1 with a covariance of 0.9. And so because I made these 1, that means that's the phenotypic correlation. And yeah, that's right. And let's standardize things so we've got a mean of 0. So it's a nice elliptical pattern. It's Adam and I like to call these cigars. Not that I don't think either of us smoke cigars, right? No, we don't. But we like to call this a cigar. And this is the 95% confidence ellipse, and here's our principal component 1, principal component 2, leading and trailing eigenvectors, if you like. I've exerted some selection, and then here's the distribution after selection. The mean has been shifted up by 40%. By 40%? Yeah, I guess that's right. Yeah. To 1 would be 100%. Okay, and so here's our distribution. And it now has a slightly tilted axis compared to what it was before. There's been a contraction in variance, quite a dramatic one, and a shift so that the covariance is strikingly less than it was before. Okay, but the correlation after selection is 0.9. All right. So now in terms of we're going to generalize all of our measures of selection to the bivariate case and apply them just to see what sorts of values we would get. And now, when we look at S, the selection differential, we're going to call it the directional selection differential because we're going to distinguish. We got a change in variances that we're going to also call the selection differential. It's a vector. It's a covariance. It's a vector of covariances. It's a shift in a mean. It's a shift in two means, in the mean of trait 1 and the mean of trait 2, S1, S2. That's the vector representation. It's a little red arrow that happens to look like this, right? Okay? Your mind is taking a screenshot. Got it? Say yes. That helps wake you up. Wait a minute, louder. Got it. Okay. I'm trying to keep us awake till lunch. All right, now we're going to talk more deeply about, we're going to talk, what happened here? Maybe if I put this up here, the online people can hear me. Let's talk more deeply about beta, which we're now going to call the directional selection gradient, and not just now for the rest of our time together. Now, if you'll recall, beta is the product of a matrix inverse and S. And here, what do we see here? This is a variance-covariance matrix. So what is beta doing compared to S? We immediately suspect that it's somehow correcting for the covariances among the traits. This is a general feature in multivariate stat. And actually, to see what's going on, I'm going to show you a little trick, because you can look at the elements of a matrix inverse, but it's a little bit painful. It's more intuitive to look at the elements of the matrices before they've been inverted. So let's do the following thing. Let's pre-multiply each of these terms by P, right? So if we do that, if we look at P beta, and then we pre-multiply this side by P, we get S, right? Because P times P inverse, that's like taking 1 times 1 over, let's say, X times 1 over X in the scalar case. We get 1, and here we get the diagonal we get a diagonal matrix, the identity matrix I, multiply that by S, we get S. So in other words, by that little operation converts this equation to this equation, S equals P beta. So why should we do this? Now this tells us about the composition of the terms that make up each of the elements in the S vector, S1 and S2. Here's our multiplication. This row times that column gives us two terms. S1 is equal to P11 times beta 1 plus P12 times beta 2. Does that ring any bells? It's kind of like the two terms of our direct and our correlated response to selection. But now we've got P matrices instead of G matrices here. And so, I'm forgetting, this is the direct effect of the selection of, so let me put it this way, let me read it to you. This term is the direct effect of selection on trait 1 on trait 2. A little bit of the tongue twister. But look at this trait. This is the indirect effect of selection on trait 2 acting through the covariance P12 on trait 1, right? So, and if we had more traits, then this would just go on and on, right? We could have a lot of others. So the point is, there's a lot of ambiguity to what S1 means. Very easy to calculate, but it could have a lot of terms. The direct term, which is sort of the intuitive one, the shift in the mean resulting from direct selection on that trait. But there could be a lot of contributions. Here there's just one because there's one other trait. But if there were other correlated traits, there would be many contributions of shifts in the mean coming from these indirect effects of selection on correlated traits. Yeah?
Should one of the off diagonals be beta 1?
I didn't know, did I write something wrong?
Yeah, you did. You got more twos than ones.
Oh yeah. Good for you, good for you. So this should be beta, let's see, no, wait a minute.
Yeah, I think so.
This should be beta, let's see, beta 2.
No, I think the first thing you put into is right.
Beta 1, let me redo the math.
Lower left one.
Oh yeah, this should be beta 1, right? Is that what you said?
Yeah.
Because it should be this times this plus this times this. So, okay. So I put that in there on purpose so that, good for you. Okay, gold star. All right, I'm glad you're paying attention back there. All right, so that's the sense in which we get the direct effects of selection if we look at beta. Okay, why does this distinction between S and B matter? And conceptually it should, but here's an example from the Price et al. Study of selection in Galapagos finches, the references coming up. So here we are in there's an episode of selection in 1976-77, and they estimated Trevor and a team that included Lyle Gibbs and maybe Dolph Schluter, can't remember who else. Selection differentials, and I haven't showed you the significance, but here's the selection differentials, all look positive on weight, beak length, beak depth, beak width. But when you look at the betas, it turns out that selection, the direct selection on beak width, accounting for correlations with other characters, is actually in the opposite direction, although the same magnitude, right? So it completely changes your perspective on how selection is acting when you correct for the correlations between the characters. So it very much does matter. This one becomes non-significant, drops out of significance when you look at the correct for correlations. I think we're in pretty good shape here. Shall we pause for a question or two? I'm sort of screaming along. Yeah.
Microphones.
Thank you. Yeah. I was thinking about the standardized selection gradients.
Yeah.
Most of them are pretty small. But it's not only because with large selection gradients, for example, 2 standard deviation or something like that,
Yeah.
you wiped out almost all the population.
You wipe out all the what?
All the population. If you think about fitness in terms of survival,
Yeah, that's
so
right, that's
it's
right.
both difficult to observe,
Right.
and then it's pretty unlikely because you've got a
Right.
dramatic reduction in just one generation of the.
But I'm going to show you a distribution of beta estimates from many field studies, and you'll see what that, basically what it's going to show is we're going to be slammed right up against 0. I mean, betas that strong are very rarely observed. It's going to be a negative exponential distribution. So, but you make a good point. Yeah. And we'll see actually the relationship to beta to selection surfaces coming up. So, yeah, you could calculate with that easily with that surface view. You could see how much fitness loss would go with a big beta. Another question?
So if you have balancing selection or directional selection, then there's no S, or I guess it's not as easy to see what S is. How would you accommodate that?
So, still works. Still
But if
works.
you have,
If you have balancing selection, I'm calling that disruptive selection. You'd have an expansion in the variance, with or without. You might or might not have a shift in the mean. It's easier to see when we draw some functions in a minute.
but if S is 0,
Yeah, that's
then
right.
you're gonna multiply it by something else, and you're gonna get 0 back.
Let's go back and look at it. I see what you're saying. I want to go. You to freeze up on me here. Just want to go back a step. Let's see. Let's go here. So you're saying if S is 0. So the way I think about it is beta is driving things. S is just the mirage. But you're saying let S1 be 0, right? Is that what you just said? So, but look at what can happen. You can get 0 because this is positive and that's negative, right? Or because any linear combination of terms like that is 0. It doesn't necessarily mean that there isn't selection going on in the way we're looking at things. Okay? But that's a good point. S0, it could be that there's no selection on anything, or it could mean that you've got opposing contributions of directional selection and they just cancel out. Yeah. There should be.
So I'm a visual learner, so I understand the S as a vector on our little cigar. That
Yeah,
made sense.
uh-huh.
If you had to think about beta in a visual way, what would it look like?
You know what? I'm visual too, and that's why we're going, exactly one of the reasons we're going to surfaces. And I'm going to need a surface to show you beta in general.
Okay.
Okay? Coming up. I feel your pain, and we will assuage your pain in due course.
Just to clarify a point here. So if you have the P matrix and the selection differential, you can just calculate the gradients, right?
You could, yeah.
Is there a catch? Because the
If you have
differentials.
samples before and after selection,
Okay.
and you can, and remember, P's easy. It's the variance covariance before selection. Usually that's where your large sample is. But you could solve just by this linear algebra for beta. Sometimes in our paper in '83, Landy and Arnold, we talk about so-called cross-sectional studies of selection. So, for example, sometimes you have a sample of individuals before selection, and then you have another set of individuals that you sample after selection. But you don't know the history of the individuals, if you see what I'm saying. So you're cross-sectional in the sense you take a snapshot then and a snapshot here, and you say, if I knew what the fates of the individuals in the original sample were, it would be faithfully represented by this sample. Without knowing those trajectories, you could solve for S, and you could do a cross-sectional analysis and estimate P this way. Now, the other way to do it is actually to know the fitness of each individual. That's what we're call a longitudinal analysis, and that's what we're going to do as an estimation exercise. So you're fraught with additional assumptions doing this in general, but you certainly can do it. It's a gift of the algebra, a nice gift. Okay, so now we're very close to our final topic, and this is a little hard to see, isn't it? So we're going to look at the nonlinear selection gradient, and we're looking at here the bivariate and general cases of C. I think what I want to do here is, let me see if I can, let's see if I can blow this up a little bit. So if I come down here and do this, whoa, right? You can see this across the internet. Okay, so here's P and here's P star. Let's see, what am I doing here? We're looking at the matrix representations, the integral representations. And we're headed, now we're going to take the difference between these and look at C. Just scroll down. And here's the reason I'm doing this. Here now is the form that S takes, because S is the vector S1, S2, and then we're post-multiplying it by the row vector S1, S2. And when you do that, you get S1 squared, S2 squared, but you also get an off-diagonal element S1, S2. S1, S2, yeah, is a product, okay? And so then when we think about what C, the selection differential, now it's a matrix, right? And it has these two terms. I just showed you this term. So when we look at it, it has terms like that, right? What is this? These are the changes in the variance. We saw those in the univariate case. These are the changes in the covariance, right? It's analogous, the covariance after selection minus the covariance before selection, and then a correction term for how much the covariance was changed by linear selection. It's now a product of two selection differentials. We could have anticipated that coming. And the point of doing that is that now we have C as a matrix of covariances, which is going to be important to us. Oops. Oh, what did I do? I see I went. We're almost, where are we here? All right. Wasted some time here. Okay, so that's what C is in general. Okay, now we're going to do our product here, and I guess I'm going to leave it this big. What is gamma? Gamma is big equals, triple equals, defined as C with a pre and post correction for correlations between the characters. Now, in the world of quadratic forms, this should be P minus 1 transform, but that's the same as this, right? So that's why we lost our T. Anyway, so this is the definition of gamma. And so the point is, gamma is the change in variances corrected for the indirect effects of selection. Okay, so we're going to do the same thing as before. We're going to take gamma and we're going to pre and post multiply, because we don't want to look at these inverse headache matrices. We want to look at regular matrices, and so to get this into an interpretable form, we're going to pre and post multiply gamma by P. And when we do that, on this side of the equation, that becomes C, and this side becomes P gamma P, right? Not so hard. And now here it is. But now when we multiply this out, just as when we did this before in the case of S, now in the case of beta, now we can see the direct and correlated, the direct and indirect effects of selection. So now when we look at the simple change in the variance, let's see, where is it? Think about what I'm doing here. This is C. When I took I haven't shown this for you. This element of C, this one right here, is the change in variance due to direct and indirect effects. And so there's effect of direct selection exerted by gamma 1,1 on the trait variance. And then there are indirect effects coming from gamma 1,2, the contraction in covariance, and also the change or expansion in covariance, and also the direct change in variance resulting from selection, right? So here's the direct effect, and here are the indirect effects of other forms of stabilizing selection. So what are we saying? This is a way of saying that gamma corrects for the correlation between characters when we look at selection effects on variance and covariance. But we've got to pre and post multiply by an inverse variance covariance matrix to make that correction, and it's completely understandable. And so what we end up with is a perspective on gamma in which we can say, these are the terms, the direct effects of selection on variance. These are the direct effects of selection on covariance. And if we're interested in morphological integration, these are the terms that interest us, because these are the terms that are describing the direct effects of selection that will promote, say, covariance and correlation between traits when gamma 1,2 is positive. Okay, so I'm sort of going fast, but I want to keep us on schedule. And so, if we look at surveys, just looking at standardized selection. So this is a distribution of standardized betas, and this is what I was alluding to a little while ago. We have that same kind of negative exponential distribution. So, values of beta that, now I've standardized the traits so they have a unit phenotypic variance before selection, so that these are the effects of beta are in units of phenotypic standard deviation. And so effects on the standardized scale, beta is greater than having a direct effect of the mean of shifting it by more than half a standard deviation, relatively rare. And most betas are having a less than 10% effect on the mean. We looked at direct selection. And then there's the Arnold. The other graph is saying the same thing. I like it, but you might not. Okay, and I haven't done a survey of gammas for. We'll talk about. I'll show you a survey later. There's a reason why I didn't include them here, because it involves too much discussion, too much niggly, nagging detail. Okay, here's what we've learned. The additive genetic variance covariance matrix is the key to understanding multivariate resemblance between parents and offspring. Not a big surprise, but nice to know. And consequently, the G matrix is the key to modeling multivariate responses to selection. And well, we have to think back to our cue ball and so forth, right? We need to take. We don't have a ball. We've got some kind of egg, in general, egg or elliptical thing that's. So the other thing that we've seen is this G induces correlated responses to selection that may be non-intuitive. Seems like the wrong set of conclusions. You know what I think I forgot to do here? Yeah, there was a step at which I meant to come to this slide and give you the lessons learned from this lecture, and I used the slide from the last lecture, and I never did that. But I did that on purpose. Because that's your homework assignment. It's actually my homework. It's actually my homework assignment. I could do it on the fly. So what we've learned, is that when we have multiple traits, we need to correct for the correlations between characters, because they introduce these not correlated effects, we're going to call them indirect effects of selection. So our simple selection differentials, shifts in mean, shifts in variance, even when we do the correction, are completely ambiguous because they don't correct for the actual targets of selection acting on correlated traits. And so although we've got this painful to look at multivariate algebra, we can devise coefficients of selection beta and gamma that do these these correlation covariance corrections. Now there's a proviso. If there's a correlated trait that's under selection and you don't include it in your vector, in your matrices, you're not going to correct for its contributions. So your analysis is unconditional. And the non-naturalist says, well, you never know. You can't have all the traits in there. And the answer is, when Peter Grant and Trevor Price tell me that, from watching the birds eat, that there's a limited number of things that are correlated with the beak that could be involved in affected by selection. It's like it's like in the old tree world when an experienced systematist shows you a phylogenetic tree, you trust that, don't you, Joe?
Once again, I was going to say something else.
All right, he's gonna. Yeah. Okay.
Yeah, I mean, it's a dilemma, but there actually is some hope because in the future sometime when we can get quantitative trait loci for all of our traits, we may be able to detect among a set of covariating traits which ones are under selection. Because if each trait affects, each QTL affects multiple traits, by looking at the shifts of QTLs, and seeing which if one trait is under selection and there's a correlated effect on another, then it's the QTLs that are shared between the two of them that you would expect to be changing, and the ones which are unique to each one, the ones unique to the secondary trait would not shift. So anyway, if you work your way through the logic, you can see that if you have that level of information, there is hope in the future. This is all off in the future. For actually figuring out which of, say, two traits that are correlated is the one that was placed under selection.
So GWAS is going to rescue us from this dilemma?
Well, I mean, you have to actually have figured out all the major QTLs, and we're a long way from being able to do that. But at least conceptually, it's possible. In other words, this dilemma is not forever.
Not forever. And also a powerful rationale for grant proposal too, presumably. But anyway, there's a proviso / dilemma here that selection people grapple with.